Morning everyone. I hope you are having a wonderful time in Sydney. So before we get started, I'd like to know how many of you actually started doing chaos already in your forms. Can I see? Raise of hands. Okay. And how many of you haven't heard of chaos yet? Okay, so yeah, I see a good mix. So before we get into chaos, so let's maybe refresh a little bit of our physics 101. So when you see these images, so what is the first thing that strikes your mind?
Equilibrium.
Yep. So yeah, right. So these are nothing but states of equilibrium. So uh, when a pendulum is in a stable state, right? So even if we apply any external stimuli, so it will come back to its original position. And in a similar way, if it is in unstable equilibrium, so it cannot come back. So like this, if we extend any system that we take, it can be in any of the states of equilibrium. So similarly, even our software systems, so they'll be in one of the state of equilibrium. So depending, they can be in stable or unstable. So when we apply any external stimuli like dependency failure or some infra failure, so there is a good chance that sometimes they come back to their original position. So that's when we stay there in stable equilibrium. Otherwise, let's say uh, there is increase in errors or latency, some cascading dependency failure, so that's when we say they are in unstable equilibrium. So just one classic example I would like to tell is, let's say we have a web service which is taking, let's say, incoming traffic, and suddenly you see a spike in requests, and you have a auto scaling system in place, but let's say if your auto scaling works as expected, everything is good, your let's say P95, P99, they won't go up. Otherwise, let's say if it doesn't work as expected, so that's when we see problems. And so as most of us are SREs, so I would like to ask this, that in the last day or two, so how many of you actually faced any incident in your forms? Yep. So I think, yeah, that's part of our day-to-day jobs. So even as you can see that we represent PayPal here. So for us, resiliency of payment process, it becomes important. So when a primary processor goes down, so we hope our let's say resiliency kicks in and secondary comes back up. But most often we see that the resilience of process and other issues that you see on the slide, like database failures or dependency failures. So when these things occur, so one thing that strikes our mind is what if there was a way to actually simulate these scenarios, so that it could actually prepare us when these things happen in production. And if there was a way to measure resiliency, so then you will know what's your system or service resiliency, and then you can actually improve on that. And most of the times what we do is we actually work with uh, distributed systems, and distributed systems by definition, they are made up of so many different components which are not reliable, but our job is to make our system reliable. So the that's where actually chaos actually helps us, but if you see the, let's say, definition of chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And so I think I hope most of us can relate to this slide, especially in the, let's say, last 2.5 years with the COVID and everything. Yep. So it's like a vaccine. Basically, we inject some harm into our systems in order to, let's say, increase the immunity. So and the main purpose of this talk is actually we started chaos journey in our firm around roughly 2 years back. And so we had a lot of learnings right from when we started and till now. So we'd like to share our journey briefly, starting with principles. How do you actually prepare in your firm, if you want to get started with chaos, and how to actually conduct experiment, which we call game day, and once you actually conduct experiment, how do you actually measure it? So, I mean, before we get there, I'd like to mention that these two books, the reference books that you see on the slides, so these are the books that we had great learnings from in our CAS journey. And one of the co-authors, Nora Jones, I think, yeah, she had a talk yesterday. So, yeah. And so if we look back at the chaos definition, right? So the three keywords being experimentation, confidence, and production, right? So the one thing, I mean, as most of us, before we became SREs, we were all at some point, most of us the software engineers. So the one question that usually strikes is, okay, how is, let's say, testing and experimentation, how they are different? Because I mean, most of the people, they usually have, let's say, strong opinions about, let's say, when it comes to breadth of testing and depth of testing. So there is some overlap, but there are some fundamental differences between testing and experimentation. So usually, testing, strictly speaking, so it doesn't create any new knowledge, and person whoever is testing the system, he most of the times knows all the, let's say, ins and outs of the system, and we usually validate, let's say, assertion, be it unit testing, regression, or integration testing. We have some assertion, and then we test whether it's valid or not. So in that sense, it doesn't create new knowledge. Whereas, let's say, if we look at the experimentation most of the times, what happens, we actually form a hypothesis, and actually once we do the experiment, we'll see whether we are actually validating that hypothesis. In that case, we are good. Otherwise, sometimes during the experiment, as we can see later in the talk, that hypothesis is not valid. So that's when we actually get some learnings, and that's a new knowledge that's created about our system. So this is like the fundamental difference. So how do we actually move the needle from testing to experimentation? How does CAS actually help bridge the gaps that are there in the testing? So CAS helps injects faults onto our system, and we should be, I mean, careful about what scenarios we pick, because there will be usually many fault, let's say, failure scenarios, and depending on the kind of service, let's say, KPIs that you have, you need to pick and choose the scenarios. And once you are done with the experiment, you need to actually measure it. So now I'll hand over to my colleague Venkat to talk about principles and.
Thank you, Sharar. Hi, everyone. So let's talk about principles of chaos engineering. So as we all know, any new discipline or technology has its own set of fundamental laws and underlying principles that govern like how the technology is applied. So similarly, chaos engineering has its own set of principles that helps us serve as guide during our experiments that we conduct. And the extent to which these principles are pursued actually directly correlates with the confidence that we can build on our distributed system. And before we get into the principles, these principles were taken from the principlesofchaos.org website, which is a community-driven GitHub page by chaos practitioners. So let's get to the principles of chaos engineering. So the first and foremost, build a hypothesis around your steady state. So what is steady state? So steady state is a measurable output of your system. So make sure you know your system and identify metrics that actually represent the state of that system. So that's your steady state. So it's that's a normal operating mode of your system. So some of the examples or metrics that we usually use are like all the golden signals, the usual golden signals like latency, throughput, errors, etc. Now, once we have this steady state defined, build a hypothesis around the steady state. So one of the common examples of that is like your SLOs. Some of the hypothesis statements that you can build are, okay, my latency will not go beyond this threshold during this experiment. So make sure, so the ideal scenario is like during chaos experiment, your steady state should not be changed. So build your hypothesis statements around that beforehand. Now the next principle is varying real world events. Now introduce some variables into your system that represent or that reflect your real world events. Like it could be some false scenarios or some disasters, etc. Now, when you are introducing these variables, like any fault, these events, any event that actually has a potential to impact your steady state is a potential variable. And these fault scenarios, prioritize them based on the impact that they generate and the frequency with which they occur. The next principle is run experiments in production. So when we first take this to any PD team, like, yeah, this is a bit controversial because, yeah, why would you want to intentionally break things in production? But the real impact of chaos, we can only see when we do things in production. So the systems, their behavior changes depending upon the environment and traffic patterns. And chaos prefers to do these experiments directly in the production. But in few scenarios, in order to build build a confidence in our system or the fault scripts that we are experimenting on, it's fine to do these experiments in a staging or QA environment first, but make sure you do this in production at some point, because that's where most of your learnings comes in. Now, whenever we say this, run experiments in production, then the next question that comes is like, how do we control our impact? So that's where the next principle comes in. So make sure you minimize your blast radius. So ensure that the fallout from these experiments are minimized and contained, like within the confines of your experiment, and have defined thresholds, like after which, like when you hit the kill switch. So make sure like you have those thresholds defined. Now, last but not the least, make sure you automate this experiment, how you are doing this experiment. So, chaos in its when you do this manual, it's not sustainable, right? So you should be able to automate this and run them continuously in order to generate the maximum output out of your chaos program. Now, this so far, like, yeah, we discussed about principles. Now let's talk about some of the common types of faults. So these are the faults that are commonly provided by almost most of the chaos platforms that are in the industry right now. So some of the common examples are infrastructure faults, application faults, database faults, or custom faults. Now, let's take an example. So infrastructure faults, like you get to play around with the CPU or memory of your host system. Or network faults is an interesting scenario, because using these faults, you'll be able to generate a very varying amount of simulations, like different scenarios you can simulate using network faults, like packet delay, packet loss, like all the latency or dependency failures, things like that. You'll be able to simulate using infrastructure faults. So far, like most of our learnings in the last few years, like we were trying infrastructure and custom faults, and yeah, we want to get to a place where we also do the application and database faults. So, and I just want to mention, like the most of the current industry platforms that are in the industry, they support custom faults, like the bring your own fault kind of a scenario, where like you'll be able to inject some of the custom scripts onto your host depending upon your needs. So there is that flexibility as well. Now, after this, like one question that comes is like, how do we prioritize these faults? Like which faults or which fault scenarios, which experiments do we do first, and which experiments we can delay later? So most of these questions can be answered by asking yourself some of these questions, like how often does a fault scenario happen, right? So, for example, there are things like version deployments which happen day in and day out, right? And there are a few things like credentials rotation or daylight saving changes. So make sure this becomes your muscle memory. So as and when you do these experiments more often, these becomes your muscle memory, and you know how to react if something goes wrong during these things. So that's how, like, prioritize those first. The next question is, how likely are you to deal with the event gracefully? There are few things which are in our control, and there are few things which are not in control. Or in other words, like, there are few things which we can afford to be as it is, like to lose the system, and there are few situations where we cannot afford to do that. Like, for example, there is a global disaster, right? So we can't do much about it, right? So if your 2 or 3 regions goes down at a time, obviously that's a very difficult scenario, but yeah, we can't do much about it. Or let's say there is a simple dependency failure, you should prioritize that faster when compared to the other scenario. And this also depends on your architecture, your system, how it is built, etc. Now, the next question that you can ask yourself is how likely is this to happen? Like, what are the imminent threats, right? So there could be some one-off scenarios like Super Bowl or elections, which do not happen very often. But there could be few other scenarios like security threats, right? So which we should be looking at immediately. So prioritize those when compared to the one-off situations. I mean, we should do everything, but how do we? This is a framework like which can help prioritize some of them first than later. Now, another interesting framework that actually helped us in the last few years, like to prioritize these faults or experiment scenarios are based on the experiment outcomes. So now we are, injecting faults. So we are actually causing some events, and because of that, there are some consequences that are happening out of our system. So if you look at the axis, like event versus consequences, and event moves from unknown to known area, and then consequences goes from unknown to known. So first, look at the known area. Like this is the use case. These are the use cases where we have complete control of the system. The experiments are, playing out exactly as we plan, right? And on the completely opposite side, we have unknown scenario where like we don't have any control of our system. Like there's a risk of losing control of the system. And in this case, like the events, like some of the consequences that are happening, we don't know why they're happening and how can we control some. And there are like the states in between, which is like known unknown, where we do have control of the system, but experiment is not playing out as expected. So, and the other scenarios. So now, usually the traditional testing practices like covers the right hand of the quadrant, like unknown and known unknown quadrant. And chaos usually, it's intended for the left-hand side of the quadrants, where like unknown scenarios. Now, but the recommendation is like to start with known, even for chaos, because this is where we get to make a lot of progress in our chaos journey, right? So this is where like you know how the system is playing out, how your events and consequences are laid out, and this is where you get to understand other aspects of our system. Like this helps us to know our system better, like build our observability, right? Make sure all your alerting mechanisms are in place, your team responses are as expected. So this is the place where you build confidence on your system and on your chaos practices. Now, once we get confidence in that, move towards unknown area. But one thing I want to say is like most of your learnings, the impact of chaos, the potential of chaos, we can only realize when we do experiments on the unknown area. Now, now we know that how to prioritize these experiments. Now let's get into some of the prerequisites before we start our chaos journey. So what are the things that we should keep in mind? So some of this we already discussed, so I'll just breeze through them. So make sure you fix all the known issues associated with your system, because once you know that there is an issue with your system, it doesn't make sense to do a chaos experiment to find out the same thing again, right? So make sure you fix all those, and then only you start your chaos journey. Now make sure all your observability is in place, because without that, it's like going in blind, so do that. And the next thing is like all your dependencies. Make sure you have a complete control or complete understanding of the dependencies and their observability as well. And obviously get the necessary approvals from leadership and stakeholders. Otherwise, we'll get into a lot of trouble. And the next one is inform operations team or not. So, this is actually depends on how you want to play around, like, right? So if you want to test a scenario, like, for example, if you want to set the SLA of your team response, like how fast your team is responding into your hypothesis, let's say, then it's better not to inform them and see how your team is responding to the events that are happening, right? But on the other hand, like if you want to look at the other aspects of your hypothesis, then inform them. And last but not the least, kill switch. So make sure you have the right abort conditions and remediation plan before you can start your chaos journey. So now that once we have these checklists completed, now let's get to the day of action, like which we usually call game day. So game day is defined as the period of time set aside to simulate a failure to test your systems, teams, and process responses. So the keywords being we are simulating a failed scenario, and that is to test your systems and processes and also how your teams are responding. Now, any game day follows through 3 different stages. Obviously, like a planning stage, and then the fault injection stage, and then post-mortem stage, which is the important one. Now, during planning, I think some of this we already discussed. So, schedule your game day well in advance, and then make sure the roles and responsibilities during your game day, make sure they're all properly set, and the relevant stakeholders are communicated about it. So, and communication is the key during chaos experiment. Now, the third one, obviously, know your system, make sure all your observability, alerting, and all your system things are like in place. And then the next one is pick scenarios and start easy, like start with known, and then move on to unknown area. Now, and the fourth one is like write down what is expected, what you expect to happen, right? So these are your hypothesis statements, and make sure like these hypothesis statements are clearly laid out so that you will be able to validate them at the end. And obviously, we already discussed like about condition skill switch. Make sure you have them. Now let's take a look at like these roles and responsibilities. So we usually use these roles, but a variation of this role, but essentially the same is applied like across the industry. So the first is chaos champion. So this person lead the game day. So he'll be the key decision maker, like when to start the experiment, when to abort the experiment, and things of that nature. So, and the next role is executioner. So this person is responsible for actually implementing and executing the experiment, like injecting a fault. And the third role is scribe. So this person takes care of all the, help others and also, take care of like documenting the hypothesis statements and also recording the results that happens. And the next role is observer. And this includes many people like, these people like help scribe and other people like to gather data and also to correlate like further reaching effects of the experiment that you are running. The next step is the fault injection scenario. So this is where you actually go and inject fault. So before you do that, like when you start injecting this fault, make sure you announce who is doing what, like what are the roles, and make sure everyone is clear of the roles and responsibilities. And communication is the key. And third, inject fault, introduce fault in the system, and then draw your observations from your observability platforms, and then roll back if needed, like if there is a need. Now let's take a deep dive into some of these areas. So the fault, usually the fault injection scenario, it starts with steady state. So make sure you have your steady state defined and identify the metrics that actually defines the steady state, right? So some of the key metrics, SLOs, things like that. So make sure they're all in the normal operating mode. Now the second step is introduce fault, obviously. So and make sure your observability reflects that, like whatever that you want to introduce. And the third, but not the least, like record observations, right? Make sure all the alerts that are supposed to be triggered, they are getting triggered, or make a note of the things that didn't go as planned. And make sure like your instant response teams are being responded as like as expected, right? So we'll like take one level down and see a case study that we have recently conducted in our organization. So this is a very common scenario like of resiliency and redundancy. So we'll just use this as an example to share some of our learnings and how we did this experiment. So, this is a common scenario where you have a service A, which is dependent on service D, right? And service D has a fallback, which is service R. And each of the service D and service R has their own fault tolerance in place, like DR endpoints in place. Now, service A usually connects to service D, and if there is an issue, then it will try to connect to service R. So there are resiliency scenarios and redundancy scenarios. Now, we want to test these two scenarios or these two simulations. So the resiliency and redundancy. So first and foremost, we'd like to simulate a scenario where we take down service D primary, and the hypothesis here is we expect service A to fall back to service D DR endpoint, right? So if service D primary is down, and obviously another hypothesis is like no errors are expected in this case. Now, So we did this experiment through packet loss. So I mean, the packet loss is a specific type of network fault injection. So using which, and when you do that, like any packets, TCP packets that are going from service A to service D primary, so we can actually, pinpoint to a certain destination and IP and port and make sure all the network packets that are going from A to D, we can make sure like they get dropped. So once we do that, like we saw that, yeah, the service A actually fall back to service D DR endpoint. Now, the second scenario that we'd like to look at it is like we want to bring down service D DR endpoint as well, and we want to see how service A reacts to that. Like, does it fall back to service R, which is our redundancy, or not? So in this case, the hypothesis is obviously service A should fall back, and no errors are expected. And another example for hypothesis here is like, what is the time that it took to fall back? Like what, and does it, and our hypothesis, like it shouldn't cross our SLA for this fallback. So same, like using the packet loss, we were able to inject faults to both the endpoints, like service D primary and DR, and we were able to simulate the scenario and the service A fall back to service R primary. So, I mean, this is actually going as expected, right? So everything is good, fallback happened properly. But there are some very critical and important learnings that we got out of this experiment. So some of the things are like, during this fallback, like even though fallback happened successfully, we identified that service D is leaking traffic. Even though it is marked down by the health checks. So, and this is due to a small bug, and because of that, service A is trying to got into this loop of connecting and reconnecting to service D, and because of that, our memory keep on piling up. So this is a very slow degradation, and we saw this impact only after 5 to 10 minutes of the fault injection. But had this occurred in production, it would have been a very nightmare scenario, like to debug what is happening and why is it happening, right? So, I mean, because we did this in a controlled environment, so we were able to proactively identify this and fix this issue before it occurred in production. And these are some of the learnings. But there are also some validations that we did as part of this experiment where like transactions that were dependent on D but cannot be replayed back on R, they failed as expected. Like this is expected, and there is actually a catch-up job that actually takes care of this, takes care of like finalizing those transactions. So that's as expected. And the service fallback time, well, like we were able to measure, and that is within the SLA. So these are some of the validations that we did as part of the experiment. And this is important because this builds confidence in your system. Like you know that next time when this happens, like the fallback will be within the SLA, and there will not be any extra failed customer interactions that could happen. Now this is where I think our post-experiment analysis comes in. So make sure you validate your hypothesis. So have your initial set of hypothesis statements and make sure you validate them at the end of your experiment. And if you see, similar to the learnings that we had, if you see any issues or any scenarios that are not played as you expected, make sure you have corrective actions as part of your postmortem, and make sure necessary tickets are in place, to track them to completion. Now, last but not the least, calculate resiliency score. Now we are doing these experiments and we are trying to understand, get the observations and trying to understand like some of the corrective actions. But how do we know, like how do we quantify this, right? So how do we know if our system is improving over a period of time? And that's where resiliency score comes in. So this is an industry metric that is being recently popularized, and many of the chaos platforms are introducing this. The resiliency score is a new feature like that helps you quantify the resiliency and fault-tolerant capacity of your system. How do we do this? So you have your initial hypothesis statements. Now, what we do is like during the experiment, we use our observability platform to validate these hypothesis statements. And how good your hypothesis statement holds, that gets translated into the resiliency score. So what do I mean by that? Now, for example, you have your application where you're conducting multiple experiments. And let's only look at the single experiment. So you have multiple hypothesis statements defined. Like let's say you have a hypothesis statement defined on latency. You have another hypothesis statement defined on errors, etc. Right? So first you look at one of the hypothesis statement, and during the fault scenario, identify how much time or how many data points like this particular hypothesis statement hold true, right, within the SLA that you previously defined. Now, give a score to that. We'll get to how we give that score. Give a score to that. And we can also have a way to give weights to these hypothesis statements depending on how important that statement is. And with that, we'll be able to take a weighted average of these scores to get the resiliency score of an experiment. And then we can do the same at the application layer as well, and have that metric over a period of time to track how the resiliency of your system is varying over a time. Just to further drill down on this. So, how do you calculate the resiliency score for a given hypothesis? So you start with your hypothesis, translate that into your query, which is based, and this depends on your observability system that you are using, and then calculate score from that. So an example for that is, let's say your hypothesis is my latency, the system's latency is going to be less than 200 milliseconds. Then translate that into your query, the query for your observability platform. It could be as simple as the average latency is going to be 200 milliseconds, right? Now, during the fault injection window, see how many of the data points fall within SLA to the total number of data points, and that actually is a measure of your resiliency score. And by the weights, we'll be able to take the weighted average of all the scores for a given experiment, of all the scores of hypothesis statements, and get the actual resiliency score for a given experiment. So this is how we calculate resiliency score. And this is an industry standard that is being introduced into many of the chaos platforms. I'll stop here and give back to Sharath to talk about the platform that we are using. It's an open source platform to conduct these experiments. Thank you.
Yeah, thanks, Santosh. So we have discussed the theory and also a practical use case, and how we have conducted a, let's say, packet loss in one of our recent game days. So the one question that must be in your mind is, okay, how did you guys do this? What platform or tool that we have used? So we actually used the Mangle by VMware. So it's an open source chaos platform. How we started is, so we had to obviously make some customizations. So we took the Mangle open source, and we made these customizations. Like first, we have some InfoSec guidelines in our form, so which actually asked us to integrate that with our ticketing system, so that all the change management is taking place. And also we the Docker let's say fault container that was there in the Mangle, so it wasn't working with our infra, so we made some Docker container related changes so that the faults actually can work on our pods. And also the network fault changes, as Venkat mentioned, right, the packet loss and all those things. So we had to make some changes there. And finally, we actually wanted to open up this platform internally in our company. So we also integrated SAML SSO with different, let's say, identity roles, so that we have the right ACLs in place when people want to execute chaos. And so this is basically a list of images. So once you set up Mangle, so you get to actually add endpoints. By endpoint, you can add a VM or a container, or let's say if you want to conduct experiments on a big scale, so you can add set of VMs as a group or set of containers as a group, and we can execute different faults like infrastructure faults, application faults, even the database related or your own custom faults. Because in at least in our firm, we observed that some of the teams they want some specific use cases to be, let's say, conducted as a fault, so they bring their own script, and we actually facilitate executing that custom fault on this environment. So so once you have Mangle set up, and running. So this is how it looks, and it also has the capability. So whenever you execute a fault and you want to look at see the history of the faults, like how many of your faults are actually succeeded or failed. So there is a process request page also where you can see the one good thing is, yeah, most of the things in this platform are extensible, so you can actually build stuff that will suit to your organization. And so the next thing is, how do we actually inject faults? Okay, so what we do is we have a service called Chaos, which is obviously built using Mangle. So we deploy that onto our control plane. So this control plane actually has access to all the different zones in our form where different applications are deployed. So and we have the connectivity in place. For example, let's say you want to inject a CPU or a memory fault on a service VM or a service part. So what is this? The bottom line is, this service eventually it injects whatever the script. Let's say if you are executing a CPU fault, there is a CPU script that is available which actually spikes up CPU, and by the time, let's say, your fault is done, your CPU comes back to normal. So by SSHing into the machine or container, we'll actually inject that. So that's how the fault is executed. And so the coming back to it's a key takeaways from this is the first and foremost, before you think of even let's say starting the chaos, know your system very well and know it's, let's say, already the known faults, and please fix them. And the other thing being, so you need to let's say prioritize your experiment, depending, let's say if it is a batch service, then throughput makes more sense than the latency. So you have to pick and choose the scenarios that you want to first perform chaos. And the one of the things that we also learned in our firm is, when you're actually, let's say, you want some application teams to in order to start your chaos journey. So that's where the usually the high friction is. So you need to convince your stakeholders of the, it's a value of the chaos. And as Venkat said, right, in order to, let's say, if we first propose them, okay, we have to run this in production, they will usually say, no, we can't do that. So that's when, let's say, you're staging our sandbox. So these are the environments where you can actually first get started, so your stakeholders also get confidence. You can check your observability whether it works everything as expected, and the leadership also, gets confidence. Then obviously you can run them in the production. At least that's the journey that we have gone through, and we were successfully able to execute in a couple of production game days. And so when do you actually start it? So most of the times what we see is we actually wait for everything to fall in place and then start chaos. So let's say if you have identified any application or system that you want to conduct chaos, and you have, let's say, a couple of main priority scenarios that you have in your back of your mind. So just choose a platform. There are many, let's say, open source platforms available and in the market. So you can choose that and obviously do any customizations as needed, and then you can get started. And usually what happens is, even we do this in our firm whenever we conduct game day. So we actually do an internal postmortem within the chaos team on any learnings from that game day, especially if you are doing any manual stuff. So figure those out and make sure that by the next game day, next experiment, you actually automate some of that stuff. Because by now what we have observed is, we are actually, conducting game days, but in order to achieve the scale, so wherever possible, we need to, automate so that you can actually bring the adoption of chaos into the firm in a faster manner, and more teams in the firm actually can practice chaos and bring value. So that comes to the, let's say, end of our talk, and these are some of the references for the principles of chaos and the couple of books that we have mentioned. And there is this Mangle GitHub IO page. As I said, right, it's open source, so feel free to contribute. And yeah, if you have any questions or comments, you can write to us. Those are our emails. And yeah, if you have any questions, please feel free to ask in the channel.